Well, hello there. So in this video, we will introduce the concept of using spectral analysis for the sampling theorem. So there are lots of reasons to do spectral analysis, which finds frequency content in signals. But in this application, we're going to be using it to find out what's the maximum frequency in a signal so that we can sample at least twice as fast as that by the sampling theorem. So if you remember, the sampling theorem says that you must sample at a faster rate than twice the highest frequency in the signal. So Fs greater than 2Fm is the sampling theorem. And this just barely works, so this is a minimum. Sometimes 20 times or something like that is a better choice. But what we're asking now is, what is Fm? How do we find the maximum frequency of a signal? If it's something like a sine wave, it just has one frequency, and that's easy. But for most signals, it's not that obvious. So the question is, what is the maximum frequency in the signal? There are two ways that we will look into that question in this class. The first one is the Fourier series. For the Fourier series, you need an analytic function, so something that we can write out as an equation, function of time. So this is good for theoretical work. The second method is the discrete Fourier transform, or the fast Fourier transform, which is the FFT. And it is for sampled data. So if we're sampling data, we can use the FFT to find the frequency content in the signal, so it's good for experimental work. But since you're dealing with sampled data in the beginning, you have to make sure that you sample fast enough to avoid any aliasing. So sometimes you'll use a fancy system to take this experimental data. Both of these analysis tools give plots as shown in these figures here. It's amplitude as a function of frequency in the signal. And so the highest frequency in the signal is wherever on this graph the amplitude goes to 0 and stays 0. So in most cases, it doesn't really go to 0, it just gets small enough to ignore. And so it's an engineering judgment what the highest frequency is, or where that amplitude is 0 to the significant figures we're interested in. If you can't sample fast enough because of your data acquisition system simply isn't fast enough for the signals you're interested in, you have an option, which is to add a filter to your system that filters out high frequency signals. So a low pass filter filters out high frequency signals. It lets any low frequency signal pass, high frequency gets filtered out. So these are usually called anti-aliasing filters when they're used for the sampling theorem. Once you determine what your sampling rate is going to be, you should, as good practice, always add an anti-aliasing filter so that you guarantee that you won't have any aliasing, because you won't have any unknown high frequency signals in your system. This is a block diagram just showing how the sensor runs into the filter, and then that goes into your data acquisition system. We'll talk about filter design in later lectures. Here's just a picture of a data acquisition system. This is a part of a schematic from a drone that I used to write software for. So I didn't design this circuit. It was designed by a friend of mine, a really good electrical engineer. And what we have is this MPX4115 barometric pressure sensor used as an altitude sensor. We talked about this in the first week of class, this particular sensor. Over here we have an op-amp in the voltage follower or buffer arrangement. So that's just separating the analog side from the data acquisition side. But right here in the middle, this is a low-pass filter. It's a very simple one with just an RC circuit, and the values of R and C are chosen for a 10 Hertz corner frequency. So anything below 10 Hertz comes through, anything above gets squashed down, which gives us an approximate maximum frequency of 10 Hertz. So with FM at 10 Hertz, what would be the minimum sample rate? I will leave that for the quiz. So this was just an introduction into the two ways we find frequency content in the signal in this class. There are other ways, but we'll look at the Fourier series and the discrete Fourier transform or the fast Fourier transform as our two methods coming up in later videos.